Okay, so unit 6, number 1, which statement is true about the graph of f of x equals 1/8 to the x power? Okay, so what I did was, in the calculator, I graphed this function, and this is what it looks like. So you could see that here it's going down the further to the right we go. Now, it looks like it stops, but it doesn't. We know that an exponential graph keeps getting lower and lower and lower and closer to the x-axis, but it's never going to touch it. Now, what I also included here was just a little portion, a little picture of a table of values. So what you'll notice is the bigger the x values are getting, the smaller the y values are getting. But if you notice the y values, right, what's happening is they're getting smaller. They're never going to reach 0. They're just going to get closer and closer and closer to a y value of 0 without actually ever reaching it. So these values are getting smaller as we go. So if we look at the answer choices, here we go. Choice 2, the graph is always decreasing. I just want to quickly go over why the other options are not the correct answer. So choice 1 says the graph is always increasing. When you look at a graph, you look at it from left to right. Our graph is not getting bigger and bigger as we go to the further to the right. Or even if you look at the y values, right? The y values are getting smaller. They are not getting bigger. So choice 1 is no good. All right, choice 2. The graph passes through the point 1, 0. Well, when x is 1, y is 0.125, not 0, so it does not pass through the point 1, 0. It looks like they were trying to trick you. Look, it goes through 0, 1, not 1, 0. So choice 3 is out. And then choice 4, the graph has an asymptote at x equals 0. So if you recall, an asymptote is a line that your graph approaches but never reaches. I usually make it a dotted line on my graph. You could see that the asymptote is right here. Okay, the x-axis is our asymptote because, as we know, our graph is going to come closer and closer to the x-axis without actually reaching it. But the equation of the x-axis is y equals 0, not x equals 0. So choice 4 doesn't work either. So again, choice 2 is our answer because the y values are decreasing as we go. Okay, number 2, they want us to graph this function. So in our calculator, we're going to go to y equals. Now remember, to get this little base on the log, we have to hit the math button. And I'm going to scroll up, it's faster than scrolling down, until we see log base. And then we can plug in base 3. And in the parentheses, we're going to plug in 2 minus x. Okay, now you get a graph if you want. See what the graph looks like. So here it is, right? We see that it appears to stop, but we know it doesn't. It's going to have a vertical asymptote. So I'm going to go to my table of values because my table of values is going to help us, sorry about that, with what points to plot. Now what you'll notice is, see right here when you get to 2 it says error. That is where our asymptote is going to be. So our asymptote is at when x equals 2. That's when we start getting an error. Now basically what you're going to do is you're going to plot any whole number points you see. So see this 1, 0, we're going to plot that. See this one, -1, 1, we're going to plot that. And if you scroll up, keep going, anytime you see a whole number point, like see there's one, -7, 2, we're going to plot it. And anything past that is not going to fit on our set of axes. So those are really the only points we're plotting. I'm going to make a quick list of them. Okay, so what I first like to do, remember, anything 2, 3, 4, and above says error, which means our graph is not going to ever reach x values of 2 or anything more. So this, at x equals 2, this is where our asymptote is. I like to actually put a dotted line where our asymptote would be. So just like that. Okay, and then what I'm going to do is I'm going to plot these points right here. Okay, so I plotted these points, and I connected them, making a nice smooth curve, and I put arrows to show that this is going to continue in both directions. And make sure you label it f of x. Also, please make sure your graph does not touch this asymptote. Here, I can write it right here, of x equals 2, but just make sure that your graph comes closer and closer to it the further to the right you go. Okay, so I'm actually looking at the questions below. They want us to state the domain. And look at this, state the equation of the asymptote. That's what we just did right here, right? The asymptote is x equals 2. So that is our asymptote. Now the domain refers to what x values our graph uses. So I'm just going to put a little d there. Now remember, along the x-axis, right? And even look at your table of values. Once we hit an x value of 2, it starts saying error. our graph is never going to reach 2. So basically, it's going to use all values lower than 2. So what we do is we say it's going to hit all the negative values, right? If you look at this arrow, doesn't it keep going to the left? The x values are going to get lower and lower. So it's going to go all the way to negative infinity. And as we work our way to the right, the x values are going to get closer and closer and closer to 2, but it's never going to reach them. So we're going to put a 2 right here. So the domain is from negative infinity until positive 2. Okay, number 3 wants us to solve this equation to the nearest 10th. All right, now I see an e in here, so we know we're going to need to use ln, but before we do, we need to get this term by itself. Okay, so in order to do that, I'm first going to get rid of this negative 123 by adding it to both sides of the equation. Okay, so that I'm just going to bring down the 4,300 times e to that power equals 5,123. Okay, now we know we need to divide by 4,300. And when we do, all right, let me just bring down the left-hand side of the equation. But on the right-hand side of the equation, if you plug in your calculator, this number divided by this number, you're going to get a decimal that just keeps going, okay? So rather than write a big, long, ugly decimal and round on our paper, might as well just leave it as a fraction because that is exact. Okay, so now we have the e by itself. So let's put an ln in front of both sides of the equation. So what that leaves us with, we know ln of e to any power leaves us with just whatever that power is. I know some of you kind of like to go like this too. All right, and then if you want to plug this in your calculator and write it as a decimal, you can, or if you want to leave it like this for now, you can. That's totally up to you. Now, if you do, let's say you plug that in your calculator, so ln of that fraction. Although you are going to have to round on your paper, which, you know, we try not to do that, but although you have to round on your paper, do not round, you know, when using the calculator. You want to take that entire answer that you see in the calculator and divide it by 0.07. You don't want to take this rounded decimal. Okay, so this is what I mean. I mean, first of all, I took ln of my fraction of my answer, and then I took my answer and divided it by 0.07. I did not take this rounded decimal and divide by 0.07. Now, I mean, this is multiple choice, so I'm sure it's not going to make much of a difference. I mean, because look at how different these answer choices are anyway. But if it was a show your work question, you want to make sure that it's rounded perfectly. Okay, so then when we did divide by 0.07, it winds up giving us approximately, right, to the nearest 10th, 2.5. So choice 2. Okay, so number 4 tells us the value of an automobile T after it was purchased is given by this function. All right, now, this is an exponential function, right? We're raising it to the exponent itself is a variable. But remember, if it's growth, right, we're adding a rate to the 1, so the number in here would be greater than 1. Since this number is less than 1 in the parentheses, it means we're seeing exponential decay. It's going down. And that makes sense, right? Doesn't the value of a car go down over time? All right, so it says which statement is true. So first of all, choice 1 and choice 3, see this word increases? There is no increase in value. Okay, remember, this number in the parentheses is less than 1. We're using 1 minus the rate. Okay, so it's going to be decreasing. So choice 1 and 3, we can cross off. Okay, now the difference between choice 2 and 4 is choice 2 says the value of the car decreases 84% each year, and choice 4 says the value of the car decreases 16% each year. Well, we want to know whatever R is, that's the rate at which it's decreasing. Now, although they have a 0.84 in the parentheses, that is not the rate at which it's decreasing. If you did 1 minus, and I'm going to do this right here, 0.16, isn't that equivalent to 0.84? So 1 minus the rate, 1 minus 0.16 is how they got this 0.84. Okay, the 0.84 is not the rate at which it's decreasing. 16% is 0.16. So choice 4 is the answer. All right, so this next one tells us that iridium-192 has a half-life of 73.83 days. So, we start off with 100 grams, and you could see they plugged it into our half-life formula here. Now, it says which equation approximates the amount of iridium-192 present after T days. So if you notice, what they did was, see how out here the exponent was T over the half-life, T over 73.83? In all of these answer choices, they got the T by itself on the outside of the parentheses. Okay, now what I did was, since we know that T over 73.83 is the same thing as, if we were to take the T and pull it to the outside, is the same thing as 1 over 73.83 T, right? You could always take that T that was on top and pull it to the outside. Now, if we want to get this T by itself on the outside of the parentheses, what we can do is we can shift this fraction right here to the inside of the parentheses as an exponent. Now, what I'm going to do to make it a little faster is I'm going to just use my eraser, and I'm just going to take this parenthesis, kind of erase some of the numbers here. Let me put those back. And I'm going to move the parenthesis right there. Okay, so now look at this. The T is all by itself on the outside of the parentheses. So from this point, it can bring everything down. But what I need to do is I need to figure out what this is equal to in the parentheses. So I'm going to plug that in my calculator. So I'm doing that as we speak. I'm typing in 1/2 to the 1 over 73.83 power. And it's telling me I get, I'm just going to round, approximately approximately 0.9906. I'm just going to stop here. 5 keeps going, so I'll just say another 6. But anyway, you could see that matches up with choice 3. So choice 3 is our answer. Okay, so number 6, Cameron puts $400 into a savings account that earns 6% annually. So we could see that. The initial amount is $400, 1 plus 6%, we'd write as 1.06 to the T power. Okay, where T is the time in years, which expression best approximates the amount of money in her account using a weekly growth rate? Okay, so first of all, weekly, how many weeks are in a year? 52, right? So if we want to calculate weekly growth rate, we're going to calculate it 52 times per year. Now, if you remember, whatever number we see here, right, whatever number we could say, how many times per year, that number is going to go in front of our T. So that's why I left a little space there when I rewrote this. But by putting a 52 in front of the T, that completely changes the value of this function. So what we do to compensate is we put its reciprocal, 1 over 52, on the inside of the parentheses. Okay, so what I did was I typed in my calculator what was in the parentheses here, 1.06 to the 1 over 52 power, and you could see that when you bring everything else down within the parentheses, I'm not going to be able to fit as much as they did in the answer choices, but I see we have, let me write as much as I can. 1.00112. That's as much as I could fit for right now. All right, so first of all, because our exponent is 52t, it has to be either choice 3 or 4. And this right here actually matches up with what we see in the calculator. I just couldn't fit it all. So choice 4 is our answer. Okay, number 7 is similar to the last one. It's just, different situation. So we're given this model right here, and D, they say, represents decades. Now, what they want us to do is they want us to change this to years, right? They want us to figure out really the decay rate in population in terms of years instead of decades. Okay, so there are 10 years in a decade, right? So basically, a year happens 10 times per decade. So this number, remember I left a little space right in front of my exponent because I'm going to insert that 10 right there. And by putting a 10 there, I have to put its reciprocal on the inside of the parentheses. Okay, so now I'm going to bring down my P equals 714. I'm plugging in my calculator right now, 0.75 to the 1/10 power, and I'm getting approximately 0.9716. Now, here's the deal. I don't see 10d in any of the exponents. What they did was they changed this in terms of y. Now, let's think about what 10d means. 10d means 10 times per decade. Okay, that's how we say that, 10 times per decade. Well, what did we say happens 10 times per decade? Doesn't a year happen 10 times per decade? So we're going to change that to a y. All right, so what choice is that? Choice 3. Okay, number 8. When observed by researchers under a microscope, a smartphone screen contained approximately 11,000 bacteria per square inch. Bacteria under normal conditions double in population every 20 minutes. All right, so I saw this word double, and that's why I put our doubling formula up here. Now it says, assuming an initial value of 11,000 bacteria, write a function, p of t, that can be used to model the population of bacteria p on a smartphone screen where t represents the time in minutes after it is first observed under a microscope. Okay, so they want us to write a function, p of t. Okay, so instead of a, we're going to substitute in p of t. All right, now we know that this number that we put in front of our parentheses represents the initial amount, and they tell us the initial amount is 11,000. And then that's going to be times 2 to the. Now, see how there's a t, p of t? We want to leave this t as a t. And it even says where t represents the time in minutes, they want you to leave it as a t. But in place of d, this stands for the doubling time period. It says here it doubles every 20 minutes. So I'm going to replace that d with a 20. And that's really all they were looking for in this part. Now in part B, it says using p of t from part A, so using this, determine algebraically to the nearest hundredth of a minute. I'm going to underline that. We don't want to lose points for rounding incorrectly, right? The amount of time it would take for a smartphone screen that was not touched or cleaned to have a population of 1 million bacteria. Okay, they want to know how long, right? So we're looking for the time. Will it take for it to reach this population? So we could plug in 1 million for p of t. All right, so let's solve. So we know we're going to have to use logs because we're solving for an exponent. So I need to get this 2 to the t over 20 power all by itself. So let's first start by dividing both sides by 11,000. All right, so on the right-hand side, the 11,000s cancel off, leaving us with 2 to the t over 20 power. Let me just move this equal sign down a little. And then on this side of the equation, I'm just going to cancel off these 3 zeros with these 3 zeros, simplifying to 1,000 over 11. And I'm going to leave it as a fraction. That way it's exact. Okay, so now this is where I can put the word log in front of both sides of the equation. I'm going to put that in parentheses. You don't need it, but I'm going to put it. Okay, and the reason I do that is so we could take our exponent and bring it to the front of the word log. So I could rewrite this right side as t over 20 times log of 2. And let me just bring down the left-hand side of the equation. All right, so far we haven't needed our calculator, but this is where we now need to use it. So we want to get this fraction by itself because this is the fraction that contains the t. So let me first get rid of the log of 2 by dividing both sides by log of 2. So on the right side, I'm left with t over 20. And this you're going to have to plug in your calculator, and you are going to have to, at this point, round on your paper. But in our calculator, we're going to use our entire answer. So when you type in log of this fraction divided by log of 2, it gives you approximately, let's just say, 6.5064. Okay, now we have to get this t by itself. So you could do one of two things. Since t is being divided by 20, the opposite of division is multiplication. You could just multiply both sides by 20. Or if you want to put this over 1, you can cross multiply, which will get you the same answer. So t times 1 is t. And if we multiply this number right here by 20, they want us to round to the nearest hundredth of a minute. So to the nearest hundredth of a minute, I'm getting 130 point, now it says 127. So that 7 would round that 2 up to a 3, so it would be 0.13. So 130.13, and the units are minutes. And there we have it. Okay, so number 9, they want us to determine to the nearest tenth of a year how long it will take for an investment to double at a 3 3/4% interest rate compounded continuously. All right, so since we see compounded continuously, we know we're using our A-PERT formula. All right, so let's take a look at what they give us. So let me bring down the equal sign and the E, and we know we're going to have to plug in numbers for everything else. All right, as far as the rate goes, 3 3/4. Now, 3 3/4, isn't that the same thing as saying 3.75, right? Isn't 3/4? Think about money. Isn't 3/4 75 cents, right? So if we took our decimal and moved it 2 places to the left, that would be 0.0375. Now, as far as the T goes, it's asking us how long. So that's what we're solving for. So I'm going to leave that as a T. Now, the problem is they don't tell us how much we're investing. It just says, how long would it take an investment to double? So you could pick whatever you want. Let's say I were to pick whatever you want, $1,000. If I wanted it to double, just multiply it by 2. So wouldn't that be 2,000 on this side of the equation? You could pick whatever number you want here and then just double it, multiply it by 2, and that's what you're going to put here. Okay, so now we're going to be solving for an exponent, and that tells us normally we use logs, but because there's an E as a base, we're going to use that specific type of log called a natural log. All right, so let's get that E by itself. So we're first going to divide both sides by 1,000. And no matter what numbers you picked, your numerator divided by the denominator will be 2, because that's what happens when you double. So we have 2 equals E to this power. All right, now, because we have E by itself, now we could throw an ln in front of both sides of the equation. All right, so that leaves us with ln of 2 equals whatever your exponent is over here. So basically, the ln cancels off with the E, and that exponent drops down and is no longer an exponent. Okay, and then to get T by itself, we're just going to divide both sides by the number in front of the T. Sorry, I'm trying to make a 7 there. So 0.0375. And it leaves us with T equals. Okay, now they want us to round to the nearest tenth of a year. So I'm plugging in my calculator right now. ln of 2 divided by 0.0375. And when I do, to the nearest tenth, it gives me 18.48, so 18.5, and the units years. So there we have it.